Why is there this shadow? Is that shadow showing up? No, it's okay. Okay, so in this video, we're going to talk about the abstract finite element, which is often called the Ciarlet triple. This was introduced by Ciarlet. So we're going to discuss about what this is, and then we'll go over two examples demonstrating what this abstract finite element is, and then we'll offer one practice problem at the end that you can do yourself. Okay? So what you need in order to be able to understand this material is you really just need some basic idea of some abstract notions in math. You know, like what is a bijection, what is a vector space, different geometrical ideas. Nothing too crazy, but at least some sort of higher understanding of math is necessary. Okay, so that's all we're going to need. And so, well, what is the finite element, this abstract finite element? Really, this idea, I'm going to be following along the definition that is introduced in Earn and Guermond. And I'll leave the citation, I'll show the citations at the end, and they'll also be in the description. But I've taken those ideas and just going to demonstrate them to you here. Okay, so let's take a look at the finite element. Okay, so this is the finite element here, which is called the Ciarlet triple. So we have three different objects which make up the finite element. Okay, so we're just going to go through them one at a time and see what they are. Okay, so the first is K. Okay, so K, well, K is some geometric shape. And typically in the finite element setting, we normally think of it as being some polyhedron. So you can think of, you know, a pyramid or a triangle, some kind of square, you know, something like that. So typically we see a polyhedron, but really in general you can work with the closure of some Lipschitz domain. So here are some examples below. A triangle is very common for finite element, but you can actually have these curved elements as well. So it doesn't have to be only straight edges. And again, we have 3D objects, and you could go 4D or higher. So K just consists of your shape, the domain you're going to be working on. Okay, and this is not the domain that you're going to be discretizing. This is the one specific element in your domain. Okay, typically what we think of as being just a finite element. Okay. So next up, we have P, and P is actually going to represent our function space. So let's go ahead and take a look. So there's not too much to say about P. P is a finite dimensional vector space of functions mapping our shape, K, to our Q. Okay, so Q can be anywhere from 1 to whatever number you want. So the idea is, well, you can also have vector valued functions. And typically, if you're familiar with the finite element method, oftentimes P is chosen to be polynomials. So you can think of some linear function, okay, or maybe a cubic function, something like that. So our object P is the space of functions mapping K to RQ. Okay, so we have K, our shape, and we have P, our function space defined on K. Okay, lastly is sigma. Okay, so this one has the most details in it, and let's go ahead and take a look at what sigma is. So sigma is a finite set of linear functionals mapping P to R. Okay, and specifically it's composed of these sigma i's. Okay, so I equals 1 to n. So we have a finite collection of these linear functionals, and they'll take in something from your space P, so say a polynomial, and they'll give you a real number. Okay, and that's the idea of a functional. If you're not sure about what a functional is, you can check out the Wikipedia page, but really it's just you're going to plug in a function in P into that functional, and it's going to give you a real number. Okay, and you know, if you've studied the finite element method any, you will often hear degrees of freedom, and so these sigma I are actually your degrees of freedom. This is what we're talking about when we bring up the degrees of freedom. Okay. And the other fact is that we require the sigma I to uniquely determine the functions in P. Okay, so for this all to make sense, for this to be a finite element, we have to have this property. And this property is referred to as unisolvence. Okay, so let's go ahead and take a look exactly at what unisolvence is. Okay, so the idea of unisolvence is, you know, we mentioned that it uniquely determines functions in P. Okay, so specifically, what that means is if you consider this mapping P to Rn, and remember n is the number of shape functions that you have, we define that mapping as such. So you plug in a function from P, capital P, into here, and we take sigma 1 of P up to sigma n of P, and we make that a vector. Okay, so for the idea of unisolvence to hold, we need that phi sigma be a bijection. Okay, and so remember, a bijection means it should be 1-to-1 and it should be onto. So every P will give you a unique value in Rn, and every vector in Rn will have a corresponding P in capital P. So if we want to prove that this mapping is a bijection, it's enough to show that the dimension of P is greater than or equal to the cardinality of sigma, and that if the sigma I of P is equal to 0 for every linear functional sigma I, then that's going to imply that your function is identically the 0 function. Okay, so if you can do this, then that will mean that phi sigma is unisolvent, which means that the Ciarlet triple that you defined is actually a finite element. Okay, so we're going to show some examples to demonstrate this fact. So this is example 1, and this is one of the most fundamental examples in the theory of finite elements, and that is our shape K is going to be this triangle, so it's a unit triangle with vertices given. The space P will be P1, so that's linear polynomials in dimension 2. Specifically, that's the span of 1, x, and y. And our space of linear functionals are given here. That is, it's the evaluation of your function at the nodes. Okay, so at the points of your triangle. And we want to prove that this is in fact a finite element. Okay, so let's go ahead and take a look. So if we want to prove this, how do we do it? Well, if we look at the dimension of P, the dimension of P is 3. Okay, so if you recall the example, it's the span of 1x and y, so that means the dimension of P is 3. And the cardinality of sigma, well, it has 3 linear functionals, which are the pointwise evaluations. Okay, so these are the same, so we are going to assume that sigma I of P is equal to 0 for all I equals to 1, 2, and 3. Okay? And P is in P1. Okay? So what does this mean? Well, if P is in P1, so since P is in P1, we can write that polynomial in some explicit way. Okay, so P is going to be some constant plus Bx plus Cy. Okay, this is the arbitrary form of the polynomial. Then sigma 1 of P equals to P of 0, comma 0, which is equal to A. Okay, sigma 2 of P is equal to P of 1, comma 0. Sigma 3 of P is equal to P of 0, comma 1. Okay, and we're going to assume that these are all 0. I think that's the assumption. So we have that A must be 0. Okay, if A is 0 and we plug in this value, well, that's going to be B. Okay, so that means B is 0. And similarly, we plug in the 0.01, we get C. And that means C is 0. Okay, so this means that P is identically 0. Therefore, the finite element, K, P, sigma, is a finite element. Okay, so that is how we demonstrate this. Okay, maybe you've seen this one before. This is the most classical. This is called the Lagrange. This is the Lagrange nodal finite element. Hopefully that's on screen. Let me see. Yeah, that's there. And maybe I'm too zoomed out. Let's zoom in a little bit. There it is. Okay, so that is how we work this out. And this example, maybe it's too simple, so I have another example we can look at. Let's check out the next one. This one's a bit more complicated. Let's go ahead and zoom in. Let's move it over here. Okay. Okay, so this next example, it's kind of messy right now, but our shape is just going to be this unit square. Okay, so you see the vertices are listed. And I've also highlighted some other features we're going to need. So I call the normal vectors on each side, n1, n2, n3, n4. And I've also labeled the sides in red. So that's s1, s2, s3, and s4. Okay, that'll be important coming up. Our function space is going to be P, so that's going to be this space here. So now if you notice, this is actually vector valued functions. Okay, so A plus Bx, C plus dy. Okay, A, B, C, D are real numbers. And our linear functionals are defined as such, so it is the dot product with the normal vector and then integrate over the side. Okay, so we are doing these line integrals about our shape function. Okay, and the question is, well, is this a finite element? Okay, and we want to prove if it is or if it is not. Okay. And also this example, it's just arbitrary. I just made up something. I don't know if it's actually used in some practical application. I just made up something for a demonstration. Okay, so let's check it out. Okay, so let's take a look. So if you recall, the dimension of our space P is actually 4. Okay. And the cardinality of sigma, there were 4 linear functionals, each one for a side of the square. Okay, so that's done. And now we want to show, we're going to assume sigma I of P is equal to 0 for I equals 1 up to 4. Okay. And so, again, since By definition of what P is, we can write P of xy, and this is a vector. I should emphasize that. This is a vector valued function. This is going to be a plus bx, comma c plus dy. Okay? And so we want to take, and I will just demonstrate one of these, and then you can fill out the details for the other. So if we look at, say, sigma 2, okay, we're assuming this is equal to 0, and sigma 2 is equal to the integral over side 2 times, of the vector p dotted with the normal vector 2 ds. Okay, so this is the boundary integral. Well, since the boundary integral, if we look back, it's just this, we're integrating across this vertical line. Okay, so x is 1, and we integrate from y equals 0 up to y equals 1. Okay, so this boundary integral simplifies a lot, so we're going to integrate from 0 to 1. P of xy, let's write out the vector, I'll write it out. This is a plus b, right, because we're integrating along x equals 1, comma, c plus dy. Okay? And then we're dotting it with the normal vector. So the normal vector here is pointing to the right, and we know that that is going to be 1, 0. Okay? So this is going to be 1, 0, dy. Okay? That means this integral becomes a plus b dy is equal to 0. Sorry, we said that over there. Okay, so we have that. So let's write here. This implies that a plus b equals to 0. Okay? And let's check maybe one more. Okay, we'll do another one. Let's say we'll do this side here. We'll do side 4. Okay, so 0 equals to sigma 4 of p. That's equal to the integral from 1 to 0 of a, comma, c plus dy. Since we are at x equals 0, we're integrating across x equals 0, dotted with the normal vector, which is minus 1, 0, and then dy. Okay, so this is the integral of negative a dy. Okay, and that is a. Okay, so that means a is 0, and if a is 0, then from our previous conclusion, we know that b is 0. Okay, so you can keep doing these. You can solve for sigma 1 and sigma 3, and you should be able to show that c and d are both 0. In which case, this finite element will be, this triple will be a finite element. Okay, I may have gone off screen there, but in any case, yeah, I went off screen. It's going to be a finite element. Okay. Lastly, I just want to provide you guys with a problem you can try for yourself. So this is an exercise, and you should determine if this is or is not a finite element. So it's a line interval. Okay, so k is this interval 0 pi, p is the span of these functions, and your sigma I functions are given here. Okay, And so you guys can go ahead and see if that is, in fact, a finite element. Okay. So again, this was based off material from Ern and Guermond, which is in the book Finite Elements 1, 2021. There's also a previous edition, which is a 2004 edition, Theory and Practice of Finite Elements. And the original idea is from Ciarlet from this paper. I'll give the links for these in the description as well. Okay. And so I think that's about it.